The RP2350 from Raspberry Pi was a very nice microcontroller already, but the 2350 learned some new tricks, and one of them is a UART-Bootloader. In this video I will show you how to use the UART-Bootloader and maybe give you some ideas what you would do in your own projects. Okay, so I have a little custom board here, and this custom board has a 2350 on it. Unfortunately, I don't have a Pico 2 here, I just have a Pico 1, but you can theoretically also do it with a Pico 2 or any other board you have. And here's the flash on this board, but we don't want to use the flash here. So if I plug this board in like this to the computer, it will do nothing. The computer will just detect it as a USB drive because it's completely unprogrammed. The flash is doing nothing. With the SDK from Raspberry Pi, you can set the Pico NO-FLASH flag to 1, and with the binary you get from there, it will just run from your RAM. The chip has 520 kilobyte of RAM, so that is a lot. I precompiled this, and I will just show you that you can go to the build and you can drag your UF2 and drag that on the RP2350, and it will, as you saw, it will just start. That is one way you can just start a binary from RAM over USB. If I unplug this, unplug it again, it will be empty again. This is one way you can have a dynamic firmware. You can just run it over USB. But there's more. So there's also a UART-Bootloader, and I just modified one of those boards, and on that board I made some modifications, but they are quite small. So I added a serial cable here that you can see, and on the flash interface I added a jumper. The jumper will set the SD1 pin to high. In addition to that, I have the one jumper at the chip select pin, which is the same as the boot button you maybe know. So here we will statically on each power up set the boot loader, and if I don't set the CS1 to high, it will just come up with a USB-Bootloader we just saw earlier. But if I set the SD1 to high, it will come up with a UART-Bootloader. And here I expose the TX and RX, which is SD2 for TX and SD3 for RX, on that serial cable. And now we will just plug it in and see what it does. And it is nothing. And over this UART cable I can now download a firmware on the chip. I wrote a small Python program, and that Python program just loads the firmware we saw earlier on the chip. I will just run it, and as you saw, it's the same thing. It blinks fast. The binary has a size of 7.4 kilobytes, and this Python program, it is open source. I will share the link in the video description. This just sends the bin file on the chip. So if we unpower it and power it again, it does nothing again. So this is dynamic, it's not programmed, it is just running. Now it's running again. So let me quickly show you what the Python script is doing. It is sending the NOC bytes. Those are defined in the datasheet, and then it will check if you send a NOP byte, which is just an ASCII N, and if the NOP byte comes back, it knows the device is there and it can just start the firmware download. Then it will open the firmware file and it will just send 32-byte chunks to the chip, And one tip from my side, don't make this mistake as well. So you always need to send 32 bytes. So at the end of your binary, you just need to send another 0 bytes. Otherwise, the chip will just do nothing. After the sending, you can also verify. So you send a clear byte, which is just you reset the address, and then you read again the file from the chip and see that it's working. You're just doing the same, but you're just verifying that it's working. This is optional, you don't need to do it. It takes some time, but you can do it. And at the end, you send the execute byte, and the execute byte just tells the chip that it should start the binary now. And that's it. This is what it's doing. And as you saw here in the terminal, the transfer of the 7.4 kilobytes took 0.118 seconds. And the verifying took almost the same time. As you can see, the previous time the downloading took a bit longer. I'm not sure why the serial cable takes a bit longer than it should be. In my blog article you can read the theoretical speed it should have, but it is a bit slower. I don't know why, but to be honest I don't care, because let's just jump to the next part. So the next step is to boot the 2350 from another microcontroller. I have a Pico W here, and it has an RP2040 on it, and I will connect it to this board, and then we will boot the 2350 from the 2040. Okay, so I connected that. We have the Pico W, but it could be any microcontroller that is speaking UART, which is basically any microcontroller. And we have the UART connected to our RP2350, and we also supply it with 3.3 volts. So I loaded a firmware on here, and if we connect this, I will show you the serial port. Yes, that's it. That was very fast. So it says hello world. It found the RP2350, that it said finished sending, and it says that it took 76 milliseconds. And then it starts to execute, and this serial is already from the remote. So it's just printing what the other RP2350 is saying. Okay, so on this Codeberg repository you can find all my software and firmware. Here's the upload.py that I showed earlier, and there's also the main and the remote controller. The remote is running on the RP2350 and the main is running on the other controller, in my case RP2040. Let's quickly take a look into it. This is the main controller. This is just derived from a Hello Serial example from Raspberry Pi, and it does basically the same as the Python earlier. It will send the knock sequence, and then it will send a NOP byte, which is basically just an ASCII N, and then check if the NOP byte comes back. And if the NOP byte comes back, it knows that the RP2350 is there, and it will break. Otherwise, this while loop will try knocking and also print that. Then we will get the pointer to the binary of the other firmware. We will take a look at this later. And for debug reasons, the address is also printed. And then 32-byte chunks are sent. And as on the Python, and don't do this mistake as well as I did it, it needs to be in 32-byte chunks. Before sending, you need to send a write byte, which is basically just an ASCII W, and then you can send your bytes to write. And that is again in a while loop. When that's finished, it will just send the execute byte, and the other controller will start running. To do is still reading the firmware. I just didn't implement it, but you can take a look on the Python. There I implemented it. It's basically very similar to the sending of the firmware. You just need to reset the address counter and then read the firmware in 32-byte chunks, and then compare it to the expected. but I did skip it here. And then in the end, it will stay in this loop and just check if there's coming something from the UART, from the other controller, and then it's just printing what the other controller is doing. Okay, so one magic is hidden here. You can read the details in my blog and also over on Stack Overflow where I got it from, but the other firmware is embedded in this firmware file, which with this trick in the CMake list. As said, here's the Stack Overflow link, you can get it from there, but basically it's just adding a resource, and that's the build binary of the remote controller, and here it's including this file remote controller.bin. This is the same as the UF2, but the UF2 is just another format, but the bin is the raw file. This is just bytes, and this raw file is embedded in the firmware of the main controller and sent via UART. This is just some magic that makes it happen that we can have a pointer to the other firmware start, we have a pointer to the other firmware end, and we get the size of the other firmware. And so here you need to encode the file name. I think you will find that similar to what we just defined in the CMake list, but you need to replace all the special characters with underscores. This is why it looks like this. I had to try this a bit, but now it works. And at the end there's start, end, and size. And this is then later used here. Yes, for the start and also for the end. I think maybe the size is not used. Yes, but we don't care. Okay, so as said, this is running on an RP2040. Should be somewhere here. Board type Pico. Yes, so that's just, sorry, here, Pico. So that's just a normal RP2040, but you can use any microcontroller that has enough storage to store the other binary and has UART and can do this with 1 megabaud. Yes, I forgot to mention this. So the baud rate is 60, so this 1 megabaud. That's relatively fast, but I think many microcontrollers can do it. Okay, so let's jump to the remote controller. This has a quite normal CMake list. It's for a Pico 2, so for RP2350. Please have in mind it will not work with the RP2040 because it doesn't have the UART-Bootloader, and it needs to have set the Pico NO-FLASH flag here, that the program is running entirely from a RAM and not from flash, because we don't have any flash. The other stuff is standard, and then we go to the C file, and there we see also UART baud rate 1 megabaud, but this can be set to any baud rate because this is the baud rate in the user mode and not in the bootloader. The bootloader rate is fixed. You could switch later on. So if the loading of the binary is finished and the chip is up and running, it could be any baud rate, higher or lower, that the chip can handle. And one special thing is here that it's not yet integrated in the Pico SDK, and I got it from a very nice colleague. You can have a look in this pull request here, who gave me a link to a GitHub where I could copy this, and this allows me to set the GPIO function here for the UART pins for the Quad SPI bank. So that is not a standard bank, and this is, as said, not yet included in the SDK, but I think the guys at Raspberry Pi will do it soon, and then you can do this just without this. Maybe it will have a differing syntax, but basically it should work similar. And there we set the GPIO pins. As said, it doesn't care if you use those pins. You don't need to use those pins because the UART-Bootloader is fixed to those pins on the Quad SPI bank. But here I want to use them also in my program, so I'm setting this. If you don't want to use those pins, you can just set it to any other pins that are easier for you to reach. But for me, I think it makes sense. I already have the connections between the two microcontrollers. It makes sense to also use those pins in the program. And just for demonstration, this is then blinking the LED and is also saying hello world from the other RP2350. And that is then in the main loop of the main controller printed to my PC here. So there's more. What if you want to run this over a longer cable? So this is a very short cable, but what if you want to do it over a longer distance? I have a solution for that as well. So UART is not very stable over a longer distance. I think you shouldn't do more than 1 meter maybe, especially because this is 1 megabaud and this is quite fast. So I built a new board. It looks like this. And it has a RS485 transceiver on it. You can see it here. This is R2 RS485 transceivers. You can ignore the part on the bottom, and it does have a RJ45 connector. And I have 2 of those boards, and I will just do UART over RS485. RS485, for those of you that don't know, is just a differential communication. Usually you're not using 100 ohm twisted pair cables as RJ45 are, but you can just do it. So let's do it over a longer cable. So here's the PQW. This is doing nothing, and now I'm plugging it in. It'll take 3 seconds. And it just worked. You saw it. I will do it once again. Can you see this? Yes. So this is now running, but if I repower it, it's not doing anything. And I'm plugging that in, and it's waiting for 3 seconds, and then it's loading, and that's just it. So that is very great. And all that over that long cable. Unfortunately, I don't have a longer cable than this, but I think in theory you could bridge quite some distance. So I think maybe 100 meters should work. Okay, so now we have it. If you like this, maybe subscribe. If you want to see what I'm doing with this and this barrel organ, you can subscribe. And if you have questions, put in the comments down below. See you next time. Bye.